Hello everybody to this what is here in the UK Wednesday afternoon session, and is a bit different wherever you are in the world. It's going to be a mixed session. Part of it is going to be an industry showcase, more about that later, but we kick off now with a long talk given by James Fairbanks, and he's going to talk about compositional scientific computing with Catlab and SemanticModels.
Great, thanks for the introduction, Bob. And I'd like to thank the organizers for giving me the opportunity to give this keynote today. And great, so I'll be talking about some work we've been doing since last time I talked at this conference last year on semantic models. And we've done a lot of work. So I think you'll find some things that are useful. Great. So there's a spectrum of scientific computing technology as I see it, where at one end you have arbitrary code where you've kind of described some system, you've built a mathematical model of the system, you've implemented a simulator for that system, and when you run the program, it solves the model. And then at the other end of the spectrum is computer algebra systems, where you describe the system mathematically as a system of equations or integral derivative equations, polynomial equations, and you want an analytic solution for the behavior of the system, right? So that's Mathematica, SymPy, tools like that. And in the middle are kind of partially symbolic tools, where it's a modeling framework that is a program that takes as input a description of the system and computes as output a simulation of the system, right? So this could be like a probabilistic programming language, a neural net modeling framework, a differential equation-based system for chemistry. And I want to see how there's the trade-off in this design space that we need to explore and can characterize. So I also think about how scientists love to make diagrams. These are selected from basically Wikipedia articles. You know, electrical circuits, signal processing pipelines, quantum electrodynamics, quantum computing. These different types of diagrams all have mathematically rigorous meaning, where the diagram isn't just a tool for understanding the math. The tool is math, or the diagram is math. So that's kind of another perspective here, and ACT helps formalize this. And I'll apologize for thunder on my audio track, in case you heard it. So the way ACT formalizes this is with syntax and semantics, and as being categories and a functor between them. So like in functional programming, the application of category theory to programming languages, your programs live in one category where you can compose them as programs. And that's probably Cartesian closed. And then you have a functor into set, the category of sets and functions, that maps every program to its denotational semantics of the mathematical function it computes, right? And then in behavioral semantics, we have a similar setup, but now the category is of designs and behaviors. So you have design for a system is a relationship between inputs and outputs. So that's kind of morphisms in, say, a hypergraph category. And then the behavior of a system is given by some functor into a category like rel, which it says that a system imposes a relation on the states of its inputs and outputs. So that's kind of perfectly analogous to programming language theory, where we've got programs that map into functions. Here we have designs that map into behaviors. And there were some good talks yesterday about model-based systems engineering, and kind of they take this approach too. So the way this is implemented in AlgebraicJulia, which is a suite of Julia packages for kind of this behavioral semantics-based modeling, is that you have algebraic structures that are theories, and they have types and terms and term constructors and axioms. And so these algebraic theories tell you how the systems work in a logical way. like a logical theory. And then you have a syntax layer where you have three mutually comprehensible syntaxes, formulas, wiring diagrams, and an embedded domain-specific language. The formulas are easiest to manipulate programmatically. The wiring diagrams are the easiest to read, and the embedded domain-specific language is easiest to write because it feels like programming. You're specifying morphisms in a category by writing programs, like you would in FP. Okay, so that's syntax. And then the instance layer is that's where it connects to Julia, where you've got values in the host programming language, in this case, Julia. You have data structures and algorithms there that work at the instance layer to manipulate these data structures. Our running example for this talk is going to be open Petri nets and dynamical systems that are given by the chemical reaction interpretation of Petri nets. So these three layers capture different aspects of kind of the ACT toolchain as I see it, from purely algebraic things in the theory, syntactical things in the syntax layer, and then the actual values that do numerical computing in the instance layer. And so how does this work for an example, say the category of natural numbers? So FinOrd, which is the skeleton of FinSet, is going to be given by, it's an instance of a category. So that's specified here. This is the definition of a category. It's a GAT theory that has objects and HOMs. And for every object, you have an identity. And for every pair of HOMs that are compatible, you can compose them. And this theory DSL is a little language for specifying algebraic theories. Then you want to map this into Julia types that are given by some data structures. So struct is just the keyword that creates data structures. And in Julia, you have FinOrd, which is going to be a natural number. So we're going to store it as an int. FinOrd funcs, which are a type of FinOrd map. You store a Julia function along with its domain and codomain as integers. So this is a function from ints to ints, and you're going to store the domain and codomain as explicitly stored integers. You have to tell Julia how to apply a FinOrd func onto a natural number. So you just call the function. And then there's another way to store them, which is as FinOrd vex, where you store the function as a vector of integers. So there, the index set of the vector is the domain, and then the entries are the images of is like the range. So it's the mapping from things in the domain into the codomain. And you still have to store the codomain explicitly in this structure. And then you have to tell Julia how to apply a FinOrd vec, and it's just you index into that vector. Okay. So that defines the instance layer, and you want to, you have to tell Julia the association you want to make between the category and the instance. So this is just saying for everything in every term constructor in the algebraic theory, what is the Julia function that it corresponds to it? So once you've done that, you can specify kind of categorical constructions of FinOrd maps. For example, you can ask, what's the initial, you have to specify these things. What's the initial object in FinOrd? It's 0. What's the coproduct of two FinOrds? Well, it's the sum and these two inclusions. So you specify, or you compute this Cospan in order to compute the coproduct. You will also need co-equalizers, and I'll specify that on the next slide because it's a little more complicated. So if you have coproducts and co-equalizers, you can define pushouts, where you take a span, FG, form the coproduct, and then ask what's the co-equalizer of the inclusions into the coproduct composed with the legs of the span. And so just reading off the definition of the universal property of coproduct tells you, okay, it's the morphism I'm looking for, U, is the co-equalizer of these composites. And so you can kind of just read right off the diagram what the code should be. So in any instance that supports co-products and co-equalizers, you have this totally generic implementation of pushout. And so you're building up categorical constructions out of the definitions. And just like a commutative diagram is a constructive, it's a construction of the thing that it's trying to prove exists. It's a constructive proof. It is also a specification of the algorithm that you use to construct it. And so I want to highlight the fact that Catlab and AlgebraicJulia are not a functional programming language embedded in Julia. The code for how to compute co-equalizers uses union find data structures and is just it's a for loop over these things, and then you union the bags with the union find data structure, and then you find the things that you're supposed to find with the union find, and you make the appropriate data structure. So we're not representing Julia programs as morphisms in a category the way that you would with Haskell, where you think of Haskell programs are morphisms in the category Hask. We're not doing that. We're writing Julia programs that have as data representations of morphisms in some other category. And I think that's a big difference in perspective that's worth paying attention to. So our example of a real application is going to be pandemic modeling, where you have perhaps, I don't know, some big outbreak of a disease and it's going to spread throughout the world, and you want to build a scientific model of this to do some planning before disaster strikes. And the development of the model needs to be fast. You need to be able to develop a model faster than the phenomena we're trying to model. And so we don't have months to wait for modeling. These are two papers from January and February talking about how to plan, say, travel and border control to help contain the coronavirus pandemic. And they're very, very quickly churned out relative to the start of the pandemic. So we want to bring that time to develop a model down from weeks to minutes. So we're going to do that. The example here is building up a model of 3 cities, each of which is going to contain an epidemic, and there's going to be a flow from one city to the next to the next. And then the goal here is like you specify it in this high-level architecture, and then you plug into each box a Petri net in order to get the composite model. So here's how we can build just the SEIR model. This is the first model of epidemics that people could think of. And you can build it in Catlab using wiring diagrams or formulas or programs. All 3 are equivalent. So here we're showing kind of transmission followed by recovery is the definition of SEIR. And so the domain are variables that come into the system. The codomain are variables that go out of the system. Then we're going to use decorated cospans to give these like semantics in open Petri nets. So you just take a functor from this category of epidemiological models, and you want to get a cospan algebra out of it to get Petri nets. And then from those Petri nets, you can generate a vector field, which is a model in open dynamical systems. So this is the system of differential equations that governs the SEIR model. So the number of susceptible people is decreasing. They're turning into infected. The number of infected people is increasing as the susceptible people come in and decreasing as they recover. So those are the 2 terms in U.2. And then the number of recovered people is growing as proportionally to the number of infected people. So that's how you get a vector field out of a SEIR model from the Petri net. And then you can compute solutions or trajectories. So we're going to call the computation of trajectories solving the model. So that's where you give it an initial condition, U0, and some rates, and a time domain that you're interested in, and it solves for these one-dimensional trajectories. Okay, so that's the pipeline. Let's break into the different steps. So the first step is to present the category of epidemiological models as a presentation of a free byproduct category. So you've got some objects, and these are the different types of states or types of species that you can have. Then you have some HOMs that are kind of your primitive reactions. So transmission, exposure, illness, recovery, death, travel. These are different things that can happen to people in this Petri net. And so every morphism in this category is going to be a system. And we're going to associate to each morphism in this category an open Petri net using decorated cospans. So here are examples of some of the primitive Petri nets on the right. This is the two species system with one reaction that encodes infection. This is exposure. And this is a kind of a spontaneous reaction where one species turns into another. And then travel, we're going to have SEI travel to SEI. So I also want to point out that the morphisms here aren't the processes in the Petri net, where you would get if you were looking at like the token game and reachability. The morphisms here are ways of attaching Petri nets using open Petri nets, right? So each morphism is a Petri net, and composition is gluing them along the common boundary. So here's how that works. You've got cospan compositions. The diagrams on the left here are the mathematical definition of how decorated cospans work. You compose cospans using this diagram on the top, where you push out the common span. Then you take that morphism U that you get from this push out, and you come over to this other diagram that's in terms of the decorators, and it tells you how to combine the decorators. You take the coproduct of the decorators, that's a decorator on the sum of the states, and then you apply this morphism, which is a morphism in set. So this diagram is a diagram in FinSet, where so these arrows are, so these objects are like numbers, and the morphisms are finite functions. And then this diagram is in set, right? So you can take sets of Petri nets to other sets of Petri nets. And then the point here is that the algorithm for composing Petri cospans is given directly by looking at these two diagrams. You compute this push out from the top diagram, take this morphism, feed it in to the functor that's given by the decorator. You have to apply the laxator on the two decorations, and you apply that morphism, and then you package it up in a new Petri cospan. So we're directly taking math as a specification of an algorithm, because they're constructive proofs, and therefore they are specifications of algorithms. So here's kind of a worked out example for the SEIR system, where you take your two cospans. So what this cospan says is, S is the first input, I is the second input for the transmission process. Then the I variable is going to get glued to the I variable in recovery. And then recovery comes out as the output here. So then the way you would compute this decorated cospan composition is embedding your two, or including your two systems into the coproduct, and then mapping according to this U to get the combined system. And so this is directly like how it works on Petri nets, and you get exactly the same story if you're working in dynamical systems, where now you have a two-dimensional dynamical system, another two-dimensional dynamical system. Their coproduct is a four-dimensional dynamical system, and then you want to quotient out by the equivalence classes given by, like U is that map into the equivalence classes. And what you do is you superimpose the tangent vectors. So that's how you get, like, in the blue system, in transmission, you're increasing the number of U2. And in the orange system, you're decreasing the number of U1s. But U2 and U1, these guys are going to become the same variable by the Cospan. So now in U2, you're increasing because of the component from U1 from transmission, and you're decreasing because of the component in recovery. So that gets us a map from EPI, which is our category of semantically meaningful epidemiological models, into Petri, and then into dynamics. And it's kind of the image of FK is the set of dynamical systems that come from valid epidemiological models. I think that's an interesting interesting way of saying, like, I don't care about solving all possible dynamical systems. I just care about solving dynamical systems that come from epidemiological models. How do you make that rigorous? And I think this is a good way of doing that. So once you have this decorated Cospan algebra, or this Cospan algebra of PetriNet decorated Cospans, you can say, for every morphism in EPI, what is the PetriNet that corresponds to it? And so now you can build models like, this is SIR, and this is SEIR, where you have this exposure term where people have an incubation period before they're infectious. And then you can say, okay, but the people who are infectious can also, they can also recover or die, or they can travel. And so you add this travel HOM in here, and that gives you this PetriNet. And so that's going to be our basic model that we're going to repeat to get our multi-city model. So this SEIRD city variable is a specification of a single city or single region epidemic. So there's like some exposure process and illness, death, recovery, travel. And the copying and merging in the byproduct category are given a kind of implicit notation. So just using a variable twice is like that. Catlab will figure out where the copies and braidings need to go in order for you to use a variable twice. And then these square brackets do the merging. So they let you specify when two variables of the same type should be merged into one variable of that type. And so this program syntax lets you write in something that looks like a functional programming language, how these things work. And then what the return value of this expression is just a Julia data structure that represents this system. So you can manipulate it with regular Julia code. So in this case, you can take powers by saying, a system raised to a power is the system you get by folding composition across n repetitions of that system. That makes sense? And Catlab will check that if you put in a system F, it's going to have to be an endomorphism because you're going to want to take powers, right? So you have to have the same domain and codomain here, and you'll get a runtime error from Catlab if that doesn't work. So Catlab kind of type checks these expressions to make sure that they're well formed. Okay, cool. So you specify this SEIRD3, and that gives you this big PetriNet. And you can see how there's repeated structure in this system, right? This subgraph is similar to this subgraph, similar to this other subgraph. And you can see that you can see the repeated structure visually. But in this way of expressing the models, that structure is explicit in the data structures. So once you have this PetriNet, you can pass to the dynamical systems and then solve them to get the time series of expected infections. So this shows that for each city, you're going to have one peak. They're going to be lagged because of the time it takes for people to travel. So they're going to have lags. And then when you superimpose these, just calculate the total, you get 3 waves of infection in the combined population. So we can also very easily, because the software is highly generic, we can say, well, if instead of having reaction rates as constants, we made the reaction rates functions of time, you can look at interventions. And so very quickly, you can talk about, well, what if we flatten the curve by reducing transmissibility? How much do we have to reduce transmissibility in order to flatten the curve by X%? So you can quickly extend your modeling framework because the code is so generic. So the high-level goal here is to connect different ways of modeling systems and solving them, which are written in high-performance Julia code, to different types of solvers and expression languages for describing problems hierarchically. And this is mediated by category theory here in the middle. And then pivoting to where we're going next, how far can we push this? We talked just about Petri nets. I think it's obvious that open graphs, you get the same story, right? But there are lots of things in scientific computing that are like a graph plus a mathematical interpretation of that graph. So Bayesian networks or neural networks, they're like, a graph whose vertices are represented by variables and whose edges encode the causal dependence between the variables. Or in the neural network, the vertices represent vector spaces and the maps represent differentiable maps. So there's all these different modeling frameworks. They all kind of feel like a graph plus a mathematical interpretation of that graph. And so I think that we can do some ACT here to generalize everything we've done with Petri nets to this broader class of modeling frameworks. So here's how one approach that's currently implemented in Catlab called C-sets. And C-sets are based on the idea that if you have an index in category C, and you look at the functors from C into set, that gives you instances. So C is like a schema, and C sets are instances of C in set. So the example here that's really popular is graphs. So if you take this category G that has 2 parallel morphisms, so 2 objects and 2 parallel morphisms, G sets are graphs. So that this object becomes the edge set, and these are the source and target relation functions. So for every edge, there's a source vertex and a target vertex. And so you can encode this in Catlab as the theory of graphs is a presentation of a free category where the objects are V and E and the HOMs are source and target. And then you can dynamically generate a Julia type graph, which is a C-set of type theory graph. So that's a type in Julia that's parameterized by a presentation of a free category. And this type graph is dynamically generated. Then you can think of saying, okay, well now, what about this category G prop, where I have my graph part, my E, V, source, target, and then I have this other set prop where, so every edge has a property and every vertex has a property. And this just works. So you can do Petri nets this way, and I think it's pretty elegant. I wanted to hit 2 examples real quick before my time runs out. So one is compositional planning, where you have a category of CAD designs, computer-aided design, of things you want to build. And then you have a category of processes where you take the object you're trying to build and you come up with a plan for how to build it. And so those plans are morphisms in the category, in the planning morphism. The plans are morphisms in this planning category. And term rewriting on plans allows you to do things like scheduling, where you turn sequential plans into parallel plans by kind of maximizing the number of tensor products and minimizing the number of compositions. So Jade Master and Evan Patterson worked on this at Siemens, and they built this tool chain that took like a Lego CAD model and built a Minecraft simulation that built the thing that they had designed in CAD. Another example is generating SQL queries from the bicategory of relations, where you take a schema that describes, so it's basically just the CSET thing again, where you describe the schema as a category, you take instances in set as database instances, and so that's a model of how databases work. And then you get a category of relations where queries, so morphisms in the category of relations correspond to queries against that database. And so you can write a undirected wiring diagram in RHEL and get SQL queries generated from that. And so then you can just run them against, a Postgres database and actually compute these things on large data sets. So coming back full circle, we have this algebraic theory that tells you how your systems are supposed to work. From that, you generate syntaxes that let you describe systems that subscribe to that theory. And then you have instances that associate to those systems Julia data types where actual computation happens. Trying to connect all the different types of modeling frameworks to solvers that can exploit this hierarchical structure. If you have repeated subunits in your Petri net, you should be able to do some computational savings there. And then we really want to push this as far as we can go. So if our modeling framework can be described as CSATs, can we build a generic interface that lets you take any modeling framework and any modeling task and write software that's totally generic between modeling tasks and modeling frameworks? Some of the tasks are like model calibration, selection, comparison, verification, validation. So you want to use kind of categorical logic as the approach to making software better. Great, so here's the team. We're working on these projects all under the AlgebraicJulia organization, and they're Catlab, Petri, and Algebraic Relations. And people working on it are Evan, Micah, Sophie, and Andrew. And we're always looking for new collaborators and for people to help out, whether they're students or postdocs or software engineers. Hit me up on Zulip if you want to get involved. With that, I'll take questions.
So yes, there are questions. The first question was by Alice Cooper. Nice. Can we get Alice Cooper?
Yes, I'm here. I'm just asking whether the Catlab and AlgebraicJulia systems allow one to present the data for a structure and have the system automatically check whether the data satisfies the conditions that define the structure.
Right. So we think that verification is hard. And so we'd rather make things easy to specify. And so the yes/no answer to that question is no, it does not check that the axioms are actually satisfied by the things you asserted. If we just trust the user to assert things that are true. But yeah, but that's mostly because verification is hard.
Thank you.
Yes, then we have a question by Joe Denman. Joe?
Oh, I think I've asked a couple, but the most recent one, I guess, is have you tried to instantiate any of the sort of many diagrammatic or algebraic theories that have been introduced in, I guess, the category theory to date, such as, CW, ZX calculus, etc.?
Yeah, so ZX, yes, that is an instance that has been instantiated. There's a current project around kind of quantum circuit optimization that we think once they're done building Julia tools for doing that, and they're based on ZX, we should be able to make that an instance. But that's ongoing work in the Julia Quantum organization.
Are there any more questions? I'm looking here.
I've got a question.
Okay.
Hi.
Yeah.
So yes, great job on this. I'm definitely subscribing to the philosophy that that every tool has its place, right?
Yep.
And as someone who uses Haskell and Julia, where would you say are the pros and cons of using one language over the other, given an equal affinity to both?
Yeah, so I think that, so I also learned Haskell and tried to use it back in like 2012 to 2014. I thought, oh, this is great. This is the best language ever. But then I tried to do high performance numerical linear algebra and realized that you get the foreign function interface, like H matrix is the only approach, or at least it was back then. And the two language problem for numerical high performance computing is a real deal breaker for me. So I think if you're doing anything that relies on high performance computing, Julia is the only option. It's got a type system. It's got a type system that's pretty sophisticated. It's got higher order functions. So if you want to do functional style programming, you can. But then it compiles down to fast LLVM. So that's the only option for this kind of work.
That's my take on it as well. So
yeah, I think until somebody writes like state of the art higher order Runge-Kutta methods in Haskell.
Well, there are things that are happening, but I think part of it is you get a lot of cumbersome and syntax to make it do what you want to do in something like Julia. And the hassle's not worth it for this domain.
Our target audience is scientists and engineers, and kind of like GE is not going to write a turbine simulator in Haskell. It's just too foreign from the MATLAB that their electrical and mechanical engineers were trained on.
Okay, I think we can have one more question. Jules Hedges.
Yeah, Jules.
Yeah, I have a variant of the same question, which is this versus DiscoPy.
Yeah.
What's the deal? How much do they overlap? How much do they differ?
Yeah, so Evan started Catlab about 2 years prior to DiscoPy, and I think we have a lot more than just wiring diagrams. That's the obvious place to start, is like you want to draw wiring diagrams in TIX, but it's a pain, and so you're going to write a program to write wiring diagrams for you. That's where you get started, and then you're like doing full-on ACT library. I think the type system in Julia is naturally more compatible with category theory, in that there are parametric types, and there is type inference is available. It's not statically typed like Haskell or Idris or Agda, but for scientific computing, I think dynamically typed is better, just because scientists, again, don't have time to struggle with, my code doesn't compile, because they're not programmers first, they're scientists first. So they need to just run it. But yeah, that's my impression, is that.
So should DiscoPy be abandoned and merged into Catlab?
I can't tell other people how to allocate their time. But I would say that I think that Julia provides a a foundation that is more aligned with the math you're trying to do. And so doing things in Julia with multiple dispatch and the type system is going to be more fruitful. I think our code looks more like the math than you could ever make it happen, than you could ever make it look in Python, just from the constraints of the language.
Okay, on that note, we thank the team again, because we got all the pictures in front of us now.
Yeah, thank you. I appreciate your time, and I look forward to the industry session that's coming up.